Hello everyone! In this guide, we'll be making another puzzle from Genshin Impact in Miliastra Wonderland. The Sliding Stones puzzle from Tsurumi Island in Inazuma. I'll walk you through the whole process step by step, as always. Since I couldn't replicate the original symbols, I replaced them with elements, but the puzzle still works exactly the same as in Genshin. The goal is to move the elemental stones so that at the end each stone is next to its matching monument. For example, the Pyro stone has to end up near the Pyro monument, and so on. You can move stones along designated paths by interacting with them. 4 types of movements are possible, depending on the stone's current position: moving inward, moving outward, moving clockwise, and moving counterclockwise. Stones cannot pass through each other, so if another stone is blocking a direction, that movement option will have no effect. Let's start by going into the Prefab library. There are quite a few models we need to create, but a lot of them can be copy-pasted. Let's start with the stones. I chose the Thunderstone model. Each stone will have a visible elemental aura so that you can easily tell them apart, and you can optionally add decorations like elemental badges. You can freely move these decorations using the arrows to find a good spot on the model. Next, add a unit tag by clicking Add Unit Tags and then selecting Open Unit Tags Management tool. And finally, create new unit tag. I called mine Sliding Stone, but the index ID is more important here since it will be referenced in node graphs later. Then add the common components we need on the stone by clicking on the Add Common Component button. We need a tap component so that it is possible to interact with the stone, basic motion device so that the stone is able to move, and collision trigger source so that the stone is able to be detected when near the respective monument. Now, click Advanced Editing under VFX Playing. This VFX will differentiate the Pyro stone from the other elements, so I recommend picking something that has many color variations, like shields. First, make sure the VFX asset type is set to looping effects. After you finish adding VFX, go back and configure the tap component by clicking Advanced Editing. Add 4 options here and name them according to each movement the stone can make. The text limit is quite small, so you will probably need abbreviations. In my case, CW means clockwise and CCW means counterclockwise. Make the trigger option area a bit larger, so interacting with the stones is easier. Next, click Advanced Editing under Basic Motion Device and add a new motion. Do not set it to Initially Effective and set its type to Fixed Point Motion. The rest of the settings will be overridden by node graphs, so they don't really matter. you can leave everything in collision trigger source unchanged. Just make sure it's set to initially effective. Now you can copy this stone 4 more times. The only changes you need to make are the decorations, if you used any, and the VFX. Everything else will be identical. Next, we need to create our elemental monuments. Let's start with the Pyro one. I chose the Pyro Elemental Monument model. All they need is a collision trigger component. Set it to initially effective, set effective targets to objects, and increase the trigger area to a sphere with a radius of 3. You cannot simply copy the monument, because each one uses a different model, but you can copy the collision trigger settings by clicking the 3 lines in the upper right corner of the tab and choosing Copy, then pasting them into the other monuments. There is one important thing about the monuments. We need an additional custom variable on the player entity. To add it, go to the 4th tab, called Combat Preset, switch to the 2nd tab under Edit Player, and click Advanced Editing under Custom Variable. The process is the same as adding custom variables to other objects. Click Add New Variables, name it, for example Activated Monuments, set the type to integer, and set the value to 0. This variable will track how many monuments are currently activated. A monument counts as activated when the correct stone is standing next to its corresponding monument. Now, we need to create 4 types of platforms: inner far left, inner middle, inner far right, and outer platforms. The good news is that in the prefab library they're almost identical, except that the outer platform uses a different model. The real differences will come later in node graphs. For the inner platforms, I chose the stone functional platform model. This time, each platform needs 2 unit tags. The reason will become clearer in the node graph section. For now, click Add Unit Tags and, for example, name them Platform and Inward Platform or Inner Platform. Next, add a collision trigger. Set it to initially effective and set effective targets to objects. You can make the trigger area a bit larger by increasing the zoom values. You can now copy this platform 2 more times and just change the names of the new platforms. Then create the last, outer platform. It doesn't have to use a different model than the inner ones, but visually it's helpful. Its collision trigger is identical to other platforms, but instead of the inward platform tag, this one needs an outward platform tag. so that it has both platform and outward platform. Finally, we can create a prefab for the path connecting the platforms. Note that this path is purely cosmetic. The stones will be configured to move only from platform to platform, but it helps with keeping consistent distances between platforms. I chose a rectangular stone platform model for the path, with zoom values of 0.3, 0.13 and 0.2 respectively. No additional components or node graphs are needed here. Time to head to the Miliastra sandbox. All node graphs in this guide will be created in the Entity Node Graph tab. Right-click on an empty space and select Create New Node Graph. Let's start with something simple. This first set of node graphs controls which tab options are available for our stones at any given time. For example, in my setup, when a stone is on an outer platform, it can only move inward. No other option is available. So my outer platform has a node graph that disables all tab options except inwards. This node graph is pretty straightforward. We just connect the event node when entering collision trigger to 4 activate disable tab nodes with IDs 1, 2, 3 and 4. If you follow this guide, ID 1 is inward movement, ID 2 is outward movement, ID 3 is clockwise and ID 4 is counterclockwise. You can always double check your IDs in the tab component. In this case, we only want ID 1 to be active, so set activate to yes on ID 1 and set activate to no on the other 3. Mount this node graph on your outer platform by going into the Prefab library, selecting your outer platform, and going into the 4th tab and clicking on Add Node Graph. Then we need to create 3 very similar node graphs for the other platforms. The leftmost inner platform should have clockwise and inward movements disabled, the rightmost inner platform should have counterclockwise and inward movement disabled, the inner middle platform only needs inward movement disabled. Next, let's create the node graphs that will be mounted on the elemental monuments. All of these graphs will be identical except for 2 details: the special effects asset chosen in mount looping special effect node, and the prefab ID used in get entity list by specified prefab ID. This node graph looks for the matching stone within a 5-meter radius. When it finds it, it adds a VFX to the monument and adds 1 to the activated monument's custom variable we created earlier. The second part of this node graph does the opposite. When the corresponding stone leaves the collision trigger, it removes the VFX and subtracts 1 from activated monuments. Let's start by creating a when entering collision trigger node. Then connect entering entity to input 2 of an equal node and connect the result to a double branch. This part checks whether the entering entity is the pyrostone. The double branch will only resolve to yes when the pyrostone is nearby. To find the pyrostone, we will use a few query nodes. First, create a get entity location rotation node. Rotation is not important here, but location needs to be connected to center point in get entity list by specified range, and set the radius to 5. This makes the monument look in a 5-meter radius around itself for an entity described in the target entity list. To get that list, start by getting all entities on the field, then narrow that list down by using get entity list by specified prefab ID, where that prefab ID is the pyrostone's prefab ID. Since there is only one pyrostone on the field, we can just take the first value using get corresponding value from list with ID set to 0, because this node starts counting from 0 and ID 0 means the first entry. Now connect yes from the double branch to a mount looping special effect node. This node plays the chosen VFX, in my case I chose Pyro Shield, as the special effects asset. Use GY root node as the attachment point name and adjust the other settings however you like. Remember that the target entity here needs to be connected to trigger entity from when entering collision trigger node, because that represents the monument. Entering entity in this case is the stone. Next, we need to add 1 to the activated monument's custom variable. We do this with 3 nodes: get custom variable, set custom variable, and addition with a value of 1. Normally, we could connect target entity on get set custom variable directly to something from the event node, but here trigger entity is the monument and entering entity is the stone. We want to modify a variable on the player instead, so we need another way to get the player entity. To do that, use get all entities on the field, then get entity list by specified faction with faction set to 1, since that's the player's faction. You can confirm this under main menu, stage settings, and faction. Then again, take the first value from that list with get corresponding value from list node and ID 0, because we are the only player on the field. This result will be our target entity for all the getCustomVariable and setCustomVariable nodes here. After that, we can copy most of the setup, but this time start with a WhenExitingCollisionTrigger node. The only differences are we change MountLoopingSpecialEffect to ClearLoopingSpecialEffect, connect special effect instance ID into it, and change the addition node into a subtraction node, so that we subtract 1 from the variable when the stone is no longer near the monument. That's it for this node graph. Remember to mount it on the Pyro monument in the Prefab library. Then you will need to create 4 additional copies of this node graph for the other monuments. They should be identical to the Pyro monument node graph except for 2 things: the prefab ID and the special effects asset. For example, for the Hydro monument, you would paste the Hydro stone's prefab ID into the getEntityList by specified prefab ID node and choose Hydro Shield as the special effects asset. Now it's time for the most difficult part. The node graphs responsible for movement in all directions: inward, outward, clockwise and counterclockwise. Note that you don't actually need 4 separate node graphs for this, it can all be done in a single graph. For clarity though, I decided to split it into 4. Let's start with inward and outward movement. The event node here is when tab is selected, because any movement should only happen after we interact with the stone. First, we need to check whether the player chose the inward option, since our tab component has 4 possible options. We do this by connecting tab ID to input 1 of an equal node and typing 1 in input 2, because 1 corresponds to inward movement in this setup, unless you use a different order in your tab component. Then connect the result to a double branch. Next, we build a part very similar to the previous node graph. Create a getEntityLocation and rotation node, connect location to center point in getEntityList by specified range, and set radius to 5. This time, the target entity list comes from getEntityList by unit tag, and the unit tag index is the index of the inward platform, because inward movement always goes from an outer platform to an inner platform. There are no other possibilities. We can then check whether the list length equals 1 and connect the result to another double branch. This step might not strictly be required here, but it's a good habit and helps prevent errors if you ever adjust platform distances or the radius in getEntityList by specified range. Normally, this would be where we connect the double branch to an activate fixed point motion device node, but there is one more check we need. The section at the top checks if there are any other stones on the platform we want to move to. In that part, the center point comes from a getEntityLocation and rotation connected to getCorrespondingValue from list. That gives us the location of the target platform. That's why the radius there is only 1 and could even be lower. The getEntityList by unit tag at the top uses the sliding stone tag. Then we check the list length for how many stones are already on the target platform. If there are any, the final double branch resolves to yes and no movement happens. Note that the last double branch must resolve to no for the fixed point motion device to be activated. For the motion itself, target entity is taken from event source entity of the WhenTabIsSelected node. Set movement mode to uniform linear motion and speed to 2. Target location can be taken directly from getEntityLocation and rotation, but like before, you can insert a 3D vector addition node and set the y-axis to 0.5 so the stones move slightly above the ground. Set parameter type to fixed speed and movement time to 3. For outward movement, copy the inward node graph and change just 2 things. Change the tab ID in the equal node from 1 to 2, and change the unit tag index in the first getEntityList by unit tag Instead of the inward platform index, use the outward platform index. The rest of the graph stays the same. Next, let's handle clockwise and counterclockwise movement. These node graphs are a bit more complex for two reasons. First, when using getEntityList by specified range here, we will get more than one result. Second, we need a way to distinguish between left and right platforms because they are otherwise identical, and we always want clockwise movement to be truly clockwise and not random. The beginning is very similar to before. We start with when tab is selected, then check the tab ID, this time is free. Then we create three query nodes, getEntityLocation and rotation, getEntityList by specified range, with location connected to center point, and getEntityList by unit tag as our target entity list, where the unit tag index is the inward platform index, because clockwise and counterclockwise movement only happens on inner platforms. Next, we create two double branches for two possible cases. In the first case, the platform is at the far left or far right, and getEntityList by specified range finds two platforms, the one the stone is standing on and the one next to it. In the second case, the platform is somewhere in the middle, and the node finds three platforms, the current one, the clockwise neighbor, and the counterclockwise neighbor. That's why we add a getListLength node and connect it to two equal nodes with input two values of 2 and 3. Only one of these double branches will resolve to yes at any given time, because the list length cannot be both 2 and 3. Then we need one getCorresponding value from list node for each possible platform, 3 in total, with IDs 0, 1 and 2. Connect each of these to a getEntityLocation and rotation node. Now we handle left versus right, or clockwise versus counterclockwise. If you want to copy this logic, make sure you place your platforms so that platforms on the left have lower z-axis coordinates and platforms on the right have higher z-axis coordinates in the location tab. If you rotated this puzzle by 90 degrees, you would use the x-axis instead. That's why we connect each location to a split 3D vector node and compare their z components. In the case with two platforms, it's simple. Plug those z values into a less than node, connect its result to another double branch, and then connect yes and no to another pair of double branches. The tricky part is correctly identifying which platform each ID refers to, because ID 0 won't always be the closer platform, and we must correctly identify which platform had the lower z component. In the case with three platforms, instead of less than, we use an assembly list node connected to getMinimumValue from list. Again, the goal is to find the platform with the smallest z component, but getMinimumValue from list only returns the minimum value, not which platform it came from. To figure out which platform that is, we compare this minimum value to each z component using equal nodes, and connect each result to the condition of its own double branch. If, for example, the first of these double branches resolve to yes, that means the platform with ID 0 has the lowest z component, and we want to move the stone there. We do that by connecting that double branch to activate fixed point motion device, where target location comes from the first getEntityLocation and rotation node, or from a 3D vector addition node if you're lifting the stone slightly, just like before. The same idea is repeated for the second and third platforms. The last part again checks whether any stones are already on the platform we want to move to. You can copy this section from the previous graphs. The only difference is that there are 3 sets of those nodes, and the center point is connected to getEntityLocation and rotation nodes coming from getCorresponding value from list with IDs 0, 1 and 2. If you had troubles following along, don't worry. All node graphs and assets from this tutorial are uploaded to the resource center, so you can download them and inspect them directly in your editor. The good news is that you can copy the clockwise node graph to create the counterclockwise one. We only need a few small changes. First, change the tab ID in the equal node from 3 to 4. Then, instead of using less than, use greater than. Finally, instead of get minimum value from list, use get maximum value from list. Everything else stays the same. As mentioned earlier, if you want to save some space in your editor, you can also merge all of these movement graphs into a single node graph. Otherwise, just mount all 4 movement node graphs on each of your stones. Lastly, we need a node graph that settles the stage once all monuments are activated, meaning that every stone is next to its correct monument. We can do this with a when custom variable changes node. First, check that the variable name is activated monuments by typing it into an equal node and connecting the result to a double branch. Then create a get custom variable node with the same variable name and connect its value to another equal node with input 2 set to 5. Finally, connect yes from that double branch to set player settlement success status, connect player entity to event source entity, set settlement status to victory, and add a settled stage node at the end. Remember to mount this node graph on the player entity. You can do that by going to the 4th tab, Combat Preset, selecting the 3rd tab at the top and clicking Add Node Graph. And that's it for this tutorial. As mentioned before, you will find the assets and node graphs used in this video in the description to help you learn and experiment. Thank you for watching, and see you in the next video.